Hello, I'm Charles Newell of GSI Environmental, and today I'm going to shed some light about a new web-based tool that can help us manage a key legacy issue, the presence of light non-aqueous phase liquids, or LNAPLs, in the subsurface. The tool is developed by Concawe, an association of European refining companies, and it's called the Concawe LNAPL Toolbox. So what is the current state of LNAPL management? Well, the environmental remediation community has been working on this problem a long time. And some of the key concepts are that almost all the sites we work on are the legacy of past practices. We can get some of the LNAPL out, but it's very difficult to completely remove all of it. The LNAPL fate and transport is complex, but there are risk-based approaches for managing the LNAPL that seem to work really well. There's been recently some new science, new technology that give us great insights on how the LNAPL behaves down on the subsurface, but there's always been this desire for better stewardship. So in summary, I would say this is a complex issue. The key knowledge is out there, but it's diffuse, it's difficult to access. So Concawe said we need a better way to transfer LNAPL knowledge. So in March of 2020, Concawe issued this request for proposal. This is coming from their Soil and Groundwater Task Force, STF 33. They said what we want is a web-based toolbox for quantitative assessments of LNAPL risk management and remediation. And they framed it with some insights and learnings. They said there are limitations in removing the LNAPL, but LNAPL bodies are typically stable. LNAPL undergoes this weathering or this relatively new process that's been discovered, natural source zone depletion, and that the risk profiles and the composition of LNAPL can change over time. So based on that framework, they came up with these general objectives. The what, we want to provide a uniform LNAPL toolbox to make better LNAPL decisions. The why, there's a need for a quantitative assessment of LNAPL body risk management and remedial approaches. The who, focus mostly on the soil and groundwater consultants working on Concawe member sites, but also can be beneficial to site managers and also to environmental regulators. The how, transfer LNAPL knowledge and LNAPL content to the web on using the R-Shiny platform. And when, it's being introduced now, so it's available right now. Let's go through the LNAPL Toolbox architecture, and it's based on 6 key questions that site managers, consultants might ask, such as, how much LNAPL is present at a particular site? How far will the LNAPL migrate? How long will the LNAPL persist? How will the LNAPL risk change over time? Will LNAPL recovery be effective? And how can one estimate this natural source zone depletion? And then each question is broken down into 3 tiers. Tier 1 is quick info. It's an easy to understand graphic, or it's a table so people can quickly grasp a key concept. Now, on the other hand, tier 3, that's a gateway to more complex tools, information and videos about more complex models that people can use for difficult problems. But the sweet spot that Concawe was aiming for was this tier 2, models and tools and calculators that are on the web that people can run to get site-specific quantitative information about the LNAPL at their site. Now, how was it developed? We use this web-based software development tool called R-Shiny. And here's this sort of big funnel that includes the R programming language, the Python programming language, JavaScript, HTML, and there's this interactivity framework that then ties in, for some of the tools, to a geographic information system. So this was the way we programmed different models, different calculators, and in some ways a mapping tool to help people understand how much of their LNAPL is down there. And on this platform, we then developed the final tool, which looks like this. Here's the home page. There's the buttons for the 6 questions. And there are 2 ways for you to access this. The first is just go to this web tool. I'll give you the address in a little bit. That's hosted by Concawe, and you can just use it online. But note that no data is ever permanently stored on the web. You've got to download that to an Excel file or a data file, and then load that back up. That is one way to help with some of the security issues that you may have. Now, a second way is just download your own version so there's no contact with the web or the cloud at all. Finally, there is a report, the user's manual, that has a lot of more details about each individual parameter and how you can actually run all the different tools that are in the toolbox. Well, let's go to Tool 1, and I'll go through the Tier 1, Tier 2, and Tier 3 in this instance. But for Tool 1, how much NAPL is present? And for Tier 1, we want to teach people about this concept that's very familiar in the LNAPL world, but LNAPL specific volume. And using this graphic from the U.S. Interstate Technology and Regulatory Council from their LNAPL training, the idea is that if you have a site where LNAPL is in the subsurface and you wave a magic wand and magically remove the sand and the clay, all the soil, and you remove all the water, and there's only left is this layer of LNAPL, and that's this thickness. And you might think of this as the LNAPL specific volume, where all of everything else has been removed. And so in this Tier 1, we have this table where then people can enter in how much LNAPL appears to be present, and that's called the apparent LNAPL thickness, say in a groundwater monitoring well. Is it 0.1 meters, 0.3 meters, or 1 meter? And if we look on the bottom right, this says that this specific volume, how much NAPL is actually down there, for a 1 meter apparent thickness in a sand, it's about 0.3 meters. That sort of makes sense because that's generally the porosity of a sand. But on the other hand, if you have a silt, there's much less LNAPL down there, maybe only 4 centimeters. So this is one of the key points of this tool, is that at many sites, because of the geologic conditions in the subsurface, fine-grained soils can hold a lot less LNAPL than coarse-grained soils, and this table helps you understand that concept. Let's go to Tool 1 again, how much LNAPL is down there, but look at the Tier 2 model, and here's one of the key things. A lot of resources of the project were put into this tool. It's called the Multi-Site Volume and Extent Model. And here you would enter in data about your LNAPL, the density and the viscosity, or you can use typical values from lookup tables. And then you enter in at each monitoring well where there's an apparent thickness of LNAPL has been gauged or measured in that well. You put in the longitude and the latitude, and then the soil conditions, the geology of that particular location. Then the model will do these calculations and then come up with the output. So here we're looking at, there's the input screen on the top left. And if you look at the model output, it goes in and it shows, well, this is the apparent thickness that was entered by the user, say it's you. But the third column over talks about, here's this LNAPL specific volume. And you can just get this sense that there's just much less LNAPL that's down there than would be expected if you were thinking of it in terms of just how much thickness is in these monitoring wells. It's all about the geology. It's all about the capillary pressure. And this tool accounts for all that and comes up with these volumes. Then there's a simple interpolation tool, a mapping tool, where it puts your different monitoring wells out there. In this case, it says that there's about 16,000 liters in there. We'll also give you indications of how much of that might be recoverable. So that's the Tool 1, Tier 2, LNAPL multi-site volume and extent model. Let's go to Tier 3. So in Tier 3, this is a gateway to more complex tools. And in this case, we're talking about how much LNAPL is present. We talk about an existing model that's more complex than our Tier 2 model, but it's called the LNAPL Distribution and Recovery Model, LDRM. It's more complex, but it's also more powerful. We have a 12-minute training video so you can get an idea of what you're getting into before diving in and downloading this model from the American Petroleum Institute. We talk about what input data you need and what it will do. In this case, it will actually simulate recovery of LNAPL from, say, hydraulic recovery, from pumping, in this case, vacuum-enhanced systems. So that's what's going on in Tier 3. It's a gateway to more complex tools. Let's go to Tool 2. How far will the LNAPL migrate? And for Tier 1, we show what I think is considered a classic LNAPL graphic, again, from the U.S. Interstate Technology and Regulatory Council, from their LNAPL training, and it shows this LNAPL body and expansion over time, which starts right at time 0, and then you can see this release. And the key point is that after about a year, that LNAPL body footprint, well, it's stabilized, and it's very typical at a lot of sites where it's just been one release that's occurred, that it takes pressure to force that LNAPL to go through these pores and the pore throats between the pores down there in the soil and the subsurface. And at some point, there's just not enough pressure, or mounding of that NAPL is not strong enough to make it go any further. In addition, there's a lot of biodegradation that's going on via this natural source zone depletion process that also helps curtail the migration. So that's what we show in Tier 1, this graphic of this picture. Oh, these LNAPL bodies, most of them are stable. Well, let's look at Tool 2, Tier 2, and here we have a new LNAPL migration model. And this was developed by Andrew Kirkman from British Petroleum, from BP, and came up with a really clever way to put in a few key input data like LNAPL transmissivity. We talk more about that in another tool where you can actually calculate it with a model. We also tell you how you can get it by using field measurements. LNAPL gradient, sort of like the slope of the water table, but instead it's the slope of the LNAPL. You can get that from maps where people plotted out the LNAPL distribution at say at your site. The natural source zone depletion rate, that's in Tool 6. We explain that, where you can get those numbers. And then once you put all this stuff in there and the current LNAPL body radius, in this example we have in here, it starts out, it's maybe a roughly 100-meter radius right now. Maybe it's going to extend a little bit farther, another 16 meters, but it's not going to get bigger and bigger and bigger over time, much bigger. Let's look at Tool 3 now. How long will the LNAPL persist? And then for this, we have a Tier 1, and we're showing a key graphic from a 2019 paper that shows trends from 1,100 LNAPL sites over 15 years. This is the ultimate data mining study from a database called GeoTracker from California. And over 15 years, it shows this blue line is the benzene concentration dropping from about 4,000 micrograms per liter. And this is the average, the median concentration of these 1,174 sites, the source concentration wells, the highest concentration wells out there. And it just drops over time, some of it from remediation and some of it from just natural attenuation. So it's almost a 90% reduction over this 15 years. So the key point is nature is very active attenuating these LNAPL sites, and you can see it in some of this data mining effort, this data right in here. Okay, let's go to Tier 2, lifetime model for LNAPL. And here we have a simple mass balance, sometimes called a box model, where you put in, this is how much LNAPL I think I have in liters, and then what the area of that is, and then this natural source zone depletion rate, that biodegradation rate that we now know is going on in the subsurface. And then there's sort of the two different models to sort of bound what that lifetime might be. And the top one assumes a constant NSZD rate over time. You can see that the LNAPL mass just gets down, and it suggests that if that rate is sustained over that time period, that the LNAPL will basically be gone by the year 2035 in this hypothetical example. But the other model says the NSZD rate decreases, and it's proportional to the LNAPL mass remaining. And it says, no, that's going to extend on beyond the year 2040. And you can change the axes to see when that was. But two different bookends in some ways to people to get an idea. There is a lot of uncertainty of how long the LNAPL will be there. But here's two ways to try to bound that particular problem. Okay, let's go to Tool 4. How will the LNAPL risk change over time? So in Tier 2, I'll just go straight to Tier 2 for this one. We have a simple LNAPL dissolution model. And this is a series of equations. It's programmed in Python. It shows up here in this tool. You put in key factors like the hydraulic conductivity and the hydraulic gradient and the width of an LNAPL lens and the thickness, and then how much LNAPL is in there. And then it will calculate or simulate the concentration that's in a monitoring well of key constituents that you enter. Typically, they're going to be things like benzene, toluene, ethylbenzene, and xylene, the BTEX compounds. But in the example, we put this in there, and as this water flows through this simulated LNAPL source zone, the mole fractions of these constituents it's getting washed out, so the concentrations go down, and you can see that over 2.5 years, this particular simulation, that benzene concentration goes down really quickly. And so you can extend and see what happens to the different constituents over time. Okay, how about tool 5? Will LNAPL recovery be effective? And here we're really talking about hydraulic recovery, drilling another well, putting a pump or a skimmer in there, and trying to move this LNAPL out. And the key thing is there enough NAPL in there where this pumping of this say fluid down in the formation, is that enough force that you can drive LNAPL to this well? And so the way this model works, another calculator in here for tier 2, is you enter the soil type, the LNAPL type, the apparent LNAPL thickness in a well, and this LNAPL gradient. Then the model calculates this LNAPL transmissivity. And so then you compare it to some of these key metrics that are, again, from this ITRC group in the US. If that LNAPL transmissivity is less than 0.0093 meters squared per day, it's less likely that LNAPL will be recoverable. Now, on the other hand, if your LNAPL transmissivity is greater than 0.074 meters squared per day, a higher number, it's more likely that, yeah, you're going to be successful. You can get quite a bit of it out. So the example here, let's say you've got a well, and there's been measured by the field crews that are out there. There's 0.4 meters of gasoline in the well, but this is in a silt type unit. So the calculator says, I think that LNAPL transmissivity is only 0.0011 meters squared per day. That's less than the metric that we just talked about. Hydraulic recovery, it's not going to be able to recover that NAPL. And so, so then this is just this calculator you can use to get into the range. Now, if you want more detailed information, there are ways to actually measure that LNAPL transmissivity in the field. Tier 3 describes how you can do that. Well, let's go to the last tool. This is an area of research that I've been really involved in over the years. But how can one estimate natural source zone depletion, what we call this NSZD? So a quick overview of Tier 1, Tier 2, and Tier 3 for this tool. Tier 1, it just says what rates are seen at LNAPL sites. And this is this discovery, I'd say, over the past 10 or 15 years that at all of these hydrocarbon sites around the world, when you measure this rate, it's a lot higher than anybody thought. But typical rates can range from 2,800 to 72,000 liters of LNAPL being biodegraded per hectare per year. Now, one problem with this NSZD world is that people are using a lot of different units to reflect these rates. So for an example, you read a paper from the US, a scientific paper, it might say, hey, here's this rate in gallons per acre per year. Not very helpful, say, if you're in Europe. But we have an NSZD rate converter, which you just put those numbers in, and there it goes. It will give you that unit, something that's more tangible to people, liters per hectare per year. There are other units that people use. Some researchers say they report this is the carbon dioxide flux that's leaving the soil, and they say it's this many micromoles per meter squared per second. We can also convert that to this liters per hectare per year, and this can give you context for yes, this LNAPL is going away, and then it also you can get these numbers that you can put in some of the tools I talked about before. But we also say in Tier 3, you can also go out to your site and get these numbers itself, like get site-specific values with various different methods, and that's in Tier 3. Well, let's summarize. Let's wrap up. There are 6 tools in this web-based toolbox developed by Concawe. How much LNAPL is present? How far will the LNAPL migrate? How long will the LNAPL persist? How will LNAPL risk change over time? Will LNAPL recovery be effective? And finally, how can one estimate natural source zone depletion? Each one of these are comprised of 3 tiers, comprised of graphics, explainers, calculators, mid-level models, and databases, gateway to more powerful and complex LNAPL tools. And you can access it all right here at this tool site, where you can either use the tool itself or you can download this version from Concawe itself. So with that, I'd like to acknowledge the entire Concawe LNAPL Toolbox team, including the people who provided the LNAPL knowledge content, and the amazing software developers who wrestled with R-Shiny to get this thing up live on the web. Then, of course, hats off to Concawe, STF 33 task force, the folks who actually had the vision to do this and then worked with us to lay out this path that we could eventually develop this particular tool. And with that, we're ready for some questions if anybody has any.